Hi everybody, this is Dr. Nigro with a Physics Fundamentals screencast. This is in our series dealing with work and energy. This particular screencast is going to look at kinetic energy, potential energy, and then specifically the kinetic energy work theorem. All right, so kinetic energy we represent with Ke in our formulas. Potential energy we use a U, and then we have a little subscript here. We're going to have two different options, UG or US, where UG stands for the potential energy due to gravity, or US, which is the potential energy stored within a spring. And then the kinetic energy work theorem really could be an energy work theorem. It's how do we take work and convert it into kinetic energy? Do we convert it into motion? Or if we think about it from potential energy's point of view, how do we do work to then store potential energy for use later? So we'll look at both of those briefly. All right, so we're going to start with potential energy, which I said we use U. All right, and we should all remember that potential energy is the potential energy for motion. All right, for us, I should say. All right, there are many types of potential energy. It could be potential energy in terms of chemical reactions or chemical bonds, but we're going to focus on mechanical. All right, so there's two types of potential energy. The first one we represent with UG. All right, this is gravitational potential energy. All right, and it's the potential energy due to a height above the Earth. All right, so to calculate that value, we need three pieces of information. All right, we need to know the mass of the object, we need to know the gravitational field where we are, and then we need to know how high it is off the ground. All right, so for our units here, we're going to have kilograms times meters per second squared. There's a Newton times meters. So we got a Newton meter, which is a joule. All right, so we're going to have joules here, just like we saw with work, which makes sense because this is energy. All right, now that potential energy, that gravitational potential energy, can get converted into kinetic energy by dropping the object. All right, let's look at our second type of potential energy. All right, and that is spring potential energy. All right, I want you to think about a spring, and you're going to stretch it way out, and then you're going to let it go. What does it do? That's right, it snaps back. All right, so it goes from being perfectly still to having a lot of potential to when you release it, it snaps back. It goes into motion. Right, so similar to gravitational potential energy, where if you drop it, the object starts to move because of the height. Here, it's because of the stretch. Now, we could do it the other way. If we had a spring that had been stretched out already, we could compress the spring, and then when we release it, it snaps out. It's the same idea. It's either by stretching it out or compressing it, but when we release it, it goes back to its equilibrium position. All right, so it's potential energy due to stretching or compressing that spring. All right, the formula is going to be very familiar if you watched my variable force screencast. It's going to be equal to 1/2 the spring force constant times that displacement, the stretching or compressing squared. All right, and again, energy, so we're going to have a unit of joules here. Okay, all right, now let's talk a little bit about the other type of energy, the one we have probably all heard of, kinetic energy, right? Energy of motion. All right, so the first requirement for something to be kinetic energy is that the object is moving. All right, and the formula is one we have seen before: mass of the object times its velocity value squared is going to give us that kinetic energy. All right, so you need to have an object with matter, and it has to be in motion. You have to have a velocity value for it to be considered kinetic energy. All right, and again, we're going to have units of joules, just like we saw with potential. All right, so now let's talk about the energy work theorem. All right, the energy work theory, notice I dropped the kinetic energy. All right, that's because it could also be considered from the potential energy's point of view. All right, but basically what we say is when work is done, the object either moves, and if that happens, the work has been converted into kinetic energy, or stops moving. In that case, the work has been converted into potential energy. So you need to read the problem carefully to figure out what you're talking about. All right. If we talk about this number 1, that means that the work that's being done leads to a change in the kinetic energy of our object. Usually the object was not moving, so it had a kinetic energy initially of 0, and now it has some. But it could be the object's in motion already, and then the work is done to change that kinetic energy. All right, so in other words, we have the kinetic energy final minus the kinetic energy initial. All right, and we know what kinetic energy stands for, 1/2 mv squared. All right, so we can plug that in and then solve for V initial or V final, depending on what the problem is asking for. All right, our other option is that work is done to stop something from moving. So if we lift something to a certain height, all right, maybe that work is being done that work is converting into gravitational potential energy. So you lift an object up over your head and then you stop moving. So you've done work to lift it, and it's all potential energy. If you drop it, then that potential energy converts into kinetic and you get motion. All right, we also could have work done to produce spring potential energy. So let's say we have a spring and we're stretching it out and then we stop. So we've done work to stretch it out and we have potential spring energy until we release the spring and then it snaps back. All right, so work can also be done to produce potential energy, either gravitational or spring potential energy. But the key is if you know the work, then you can figure out what the potential or kinetic energy is of your object based on the particular situation. All right, so let's try a couple problems. All right, so an aircraft carrier has 1 times 10 to the 10th joules of kinetic energy when moving at 15 meters per second. What is the carrier's mass? All right, so this is a straight kinetic energy question. So we have kinetic energy, 1 times 10 to the 10th joules. We have a velocity of 15 meters per second, and we want to figure out, well, what is the mass of that object? All right, so our formula for kinetic energy is 1/2 mass times velocity squared. So we plug in 1 times 10 to the 10th joules equal to 1/2 of our unknown mass times 15 meters per second squared. All right, so we move things around, isolate our variable, and we end up with 8.9 times 10 to the 7th kilograms. All right, you might say, well, that's a lot. All right, but we are talking about aircraft carriers, so that seems very reasonable to me. So that's an example of using our kinetic energy formula. All right, let's see. Now we have a soccer ball with a mass of 2.5 kilograms rolling across a field at 16.5 meters per second. What is the ball's kinetic energy? All right, so this time we know the mass, 2.5 kilograms. We know the velocity, 16.5 meters per second, and we're asked to find the kinetic energy. All right, so again, kinetic energy is 1/2 mv squared. All right, this time we don't need to do any algebra rearrangement. Everything's on the same side. So 16.5 meters per second squared. So we square 16.5, multiply it by 2.5 and then by half, and we find the kinetic energy of the ball is 340 joules. All right, so those are pretty straightforward using our kinetic energy formula. All right. Now we have a soccer ball, still 2.5, and it's given an initial velocity of 8.5 meters and rolls to a stop at 10.2 meters. How much work is done on the ball? All right, so let's think about what's happening to our ball. All right, we've got our normal force, we've got our gravitational force, those are equal and opposite. The ball's rolling to the right. It doesn't say that, but that's how I always draw them. All right, but it's slowing down. There's no applied force here. All right, it's just rolling, but there is a frictional force. That's what's slowing it down. All right, so the work that we're interested in is how much work is that frictional force doing? So the work due to friction is going to be equal to the force of friction times our displacement times the cosine of our angle. All right, so we're going to need to figure out what the normal force is, which we could do. Oh, but you know what we don't have? We don't know mu. So we must be able to figure out the force due to friction or work due to friction in a different way. So let's try something different. Let's use our energy work theorem. So we know that the work that's being done is equal to the change in the kinetic energy. Why don't we approach it this way? All right. So that frictional work is equal to the final kinetic energy minus the initial kinetic energy. All right, so we're going to have 1/2 times 2.5 kilograms. Our final velocity value is 0, right, because it comes to rest, minus 1/2 times 2.5 kilograms, and our initial velocity value of 8.5 meters per second squared. All right, so if we look, all right, we've got 1/2 and 2.5 on both. Oh, this is actually goes to 0, so we don't have to worry about that. All right, so our work due to friction is going to be equal to 8.5 squared times 2.5 times 1/2. And so we find that we have 90 joules worth of work that is being done by this frictional force. Oh, and now it wants to find the force due to friction. All right, so now we're going to use our work formula. All right, so we know that that work due to friction is equal to the frictional force times our displacement times the cosine of our angle. So we have negative 90 joules equal to a frictional force that we don't know. Our displacement was 10.2 meters, and our theta angle here, because it's friction, is 180 degrees, which is a -1, right, which is great because that's going to fix our negative sign. All right, so our frictional force here has a magnitude of 8.8 newtons. Okay, so as you can tell, you need to read the problem better than I did there. You need to make sure that you have everything you need to use the formula that you want to. In my case, I tried to use the work formula with force and displacement in it, but I didn't have enough information for that. So instead, I needed to use the work energy theorem, which then let me find the work, which then let me find the force. Okay? All right, let's try this one. A 70 kilogram ice skater at rest is pushed with a 5 Newton force over a distance of 0.5 meters. What will be the resulting velocity of the skater? All right, so we've got mass, 70 kilograms. We've got an applied force of 5 newtons, and we've got a displacement of 0.5 meters. And we're looking for V final. All right, now we do know V initial because she was at rest, so I'm going to put a 0 in. So here is our unknown. All right, so when I see velocity values like this, I think kinetic energy. So I know I have mass and I have V initial, so I can find one kinetic energy. I can find my initial kinetic energy. I need to find the final kinetic energy, which means I'm going to need to use my work energy theorem. But that means I need to know the work. All right, so I'm going to start with that. My net work, not net work. It's the work done by the applied force is equal to that applied force times my displacement times the cosine of theta. All right, so I pushed horizontally, so that work is going to be equal to 5 newtons times 0.5 meters times the cosine of 0 degrees. So that's 1. So the applied work here is going to be equal to 2.5 joules. All right, now that work was used by the system to change the velocity of my skater. All right, so the work equaled a change in the kinetic energy of my skater. All right, so I know that that 2.5 joules is equal to the kinetic energy final minus the kinetic energy initial. Well, initially she wasn't moving, so that goes away. So that means the 2.5 joules is just equal to 1/2 of the mass times my V final squared. All right, so 2.5 joules is going to be equal to 1/2 of 70 kilograms times V squared. All right, so I plug that into my calculator, divide the 70 and the half over, and then take the square root, and I find that the velocity of the skater after the push is 0.27 meters per second. Okay, all right. Next, a person lifts a barbell to a height of 0.4 meters. If the barbell has a mass of 15 kilograms, how much potential energy does it have at maximum height? How much work did the person do while lifting the barbell? All right, so let's see what we have. All right, we have a height of 0.4 meters. All right, we have a mass of 15 kilograms, and we're asked to find the potential energy and then the work. So those are two unknowns. All right, now let's think about the barbell. All right, so here's my barbell. All right, I am lifting it. So here's my applied force, but I am lifting against gravity. All right, so that means this applied force has got to be equal and opposite to my gravitational force. All right, I know that because I'm holding it there. Right, so that was the force I needed to get it up there. All right, so that means that I can calculate my gravitational force using mass times gravity times height. All right, so in this case, 15 kilograms times 0.4 meters times 10 meters per second squared. All right, so we multiply that out and we have 60 joules worth of potential gravitational energy. All right, now the work energy theorem tells us that we must have done work to reach that particular value. So if the potential energy is 60, then I must have done 60 joules worth of work to get the barbell up to that height. All right, and that I could calculate using FG if I wanted to. I don't need to, but I could. Okay. All right. Here we have a crane lifting a 50 concrete slab to a certain height, doing 7,500 joules worth of work. How high did the crane lift the slab? All right, so we have a mass of 50 kilograms, and we did some work, 7,500 joules to lift it up there, and we're looking for the height. And we know that gravity is 10 meters per second squared. So here's what we know. All right. Now remember, using our work energy theorem, the work that the crane did to lift that concrete slab to this height is equal to the potential energy that the slab has at that height. All right. So that means that that potential energy must be equal to 7,500 joules, and that's equal to mass times gravity times height. So 7,500 joules equals 50 kilograms. That's a really light concrete slab. That's okay. 10 meters per second squared times our unknown height. All right, so we calculate everything out and we find that the crane lifted that slab a distance of 15 meters. All right, so again, the important part here is this work energy theorem, this idea that we did work to lift the object to this height. And once we get there, all that work is now potential energy in that object. All right, here we've got one about a spring, so that's good. A spring with a K value of 750 newtons per meter is compressed by 5 centimeters. How much work was done on the spring during the compression? All right, so we've got a K value, 750 newton meters. We've got a change in position of 5 centimeters, that's 0.05 meters. And then we're asked to find the work that was done for that compression. Okay, so we start by thinking about calculation of that work. We know that when we have a variable force like we do with springs, we're going to use our formula of 1/2 K times that displacement squared. All right, so 1/2 of 750 Newton meters times 0.05 meters squared. All right, so we find that we've done 0.938 joules worth of work. All right, how much potential energy does the spring have after the compression? All right, so when we use this 0.938 joules to compress the spring and then stopped, all that work is now sitting in the spring as potential energy. So that means that the work that we did is equal to the spring's potential energy at this moment. So that means the spring's potential energy is also equal to 0.938 joules. Again, using our work energy theorem, the idea that doing work can convert energy from motion into potential energy or convert work into kinetic energy. Okay, so when we talk about energy in terms of potential energy, it's the potential to change or convert into motion. And we can do it in terms of gravitational potential energy, which means we've lifted something to a height above the earth, or spring potential energy by compressing or expanding a spring. We can also talk about kinetic energy, which is the energy of motion, all right, which is 1/2 mv squared. And then we can talk about converting work into either kinetic energy by having an object that's not moving go into motion, or an object that is moving increase or decrease its motion. Or we can talk about taking that work and converting into potential energy by moving an object, either by lifting it or by expanding or compressing a spring, and then it is now potential energy. Okay,